Yeah, very good afternoon to all the student participants of ECEB section, second year. I welcome all of you to the next learning session, practicing session of Digital Electronics Laboratory. U19 EC 212 is the course code. Digital Electronics Lab is the course title. And where we are now standing in this, we have completed pre-lab verification of logic gates. We have completed as the prerequisite lab. Next to it, we have started implementing adder and subtractor circuits, in which we have seen four types of different circuits. One we call it as half adder, then half subtractor, full adder, and full subtractor we have implemented using Logisim simulator. By using logic gates, basic gates, how to implement them, that we have seen as the second experiment. Next to that, we have seen multiplexer, demultiplexer. Yeah, Priyadarshi. Multiplexer, demultiplexer we have covered. And that is our third experiment. I think we have taken a very long time to implement and to explain mux and demux. Okay. I think any question, whatever may be the question, whatever may be the type, that will be asked for you in the examination. I think with the idea or with the concept, what you learned about mux and demux, both in theory classes and also in laboratory sessions, I think you are in a position to explain it or to implement or to design it. Okay, we have seen 4:1 multiplexer and 1:4 demultiplexer completely. That is our third experiment. And today I am planning to start the next experiment, which is the implementation of parity generator or checker. See, as far as parity generator checker are concerned, both are one and all the same. Only thing, parity we can generate it from the sending end, and at the receiving end we can check the parity. That is the actual difference. But what we are going to implement here in our class or in our laboratory class is generator. How to generate, we will see. How to generate a parity bit. What is parity? Parity is used. What are the types of parity? That thing we will see. And parity checker, as I am telling now, we can do it in the receiving end. So it finds application. I told in the last Friday's class itself about a small info about parity. Okay. See, a parity is a type of bit. Bit. Can anyone tell what is a bit? B-I-T. It is meant by a bit. Bit na enappa full form. Yes, anyone? Yeah, Renuka Devi and Pavitra, yes, we have answered. Bit stands for binary digit. Okay. Binary digit means, as its name tells, by means two, either 0 or 1 it can be. That we call it as a bit. Then what is a byte? B-Y-T-E. B-I-T-E கிடையாது. B-Y-T. What is 1 byte? We are having ample number of terms like this. What is 1 byte? What is what we call it as a word? W-O-R-D. Then what can be called a nibble? Nibble. N-I-B-B-L-E. Pavitra, as you have given answer as 1 element. Renuka Devi is correct. I think she has answered for 1 byte. 1 byte of data. It means there are 8 bits. 8 binary bits will be there in a byte. What is a word then? Word. Priyadarshi. Byte is a computer storage. Okay, good. All these things are answers. No problem. Right? It's a computer storage. It's a kind of element, one element, Renuka Devi has said. Sorry, Pavitra has said. And 8 bits of data combined together to form a byte. Okay. Okay. What is a word? If no exact answers are there, you can guess it. No problem. What is said to be a word? WORD. 2 bytes. Excellent. Renuka Devi, you have given the correct answer again. 2 bytes of data, we call it as a word. That means how many bits? 1 byte will have 8 bits. So 2 bytes means it will have 2 into 8, 16. 16 bits of data, we are going to call it as a word. Then there is something in computer called double word. Can anyone guess how many bits and bytes will be there as far as a double word is concerned? Double word. Yeah, 32. Yeah, Priyadarshi, you are right. 32 bits will constitute a double word. Or I can say 4 bytes, okay, will be called a double word as far as, yeah, 4 bytes. Rajashri and Renuka Devi, you are right. 4 bytes of data, we are going to call it as a double word. What is a nibble? Nibble. What is a nibble? You can guess it again, no problem. How many bits will be called a nibble? Nibble. Yeah, Priyadarshi has answered it. 4 bits. Half byte, we call it as a nibble. Half byte. That means 4 bits of data, we will call it as a nibble. Okay, very good. So why we have started these things is in computers, normally the data sending and receiving will take place in the form of packets, we call it as data packets. Data will be sent like packets. Okay. So while sending the data, for example, if I am having a 8-bit data, that means 1 byte of data, I want to send it. But inside the process, while the process is happening, the sending process, there is no provision I have got to check whether whatever I have received that will be delivered as such. There is no provision for checking it. Okay. For that, what I am going to do is I'll be including a bit, extra bit. We call it as the parity bit along with the data bit. So data bit already is of 8-bit size, means I will add one more bit. We call it as a parity bit. Along with the data, I will add it and I will send to the receiving end. Okay. While receiving the data, I will check the data which I have received, which I have collected. Okay. If there is a change in the parity variant or parity type or with the parity bit, if there is any change, then I can understand that some error has taken place. So whatever you sent me has not received correctly. That is the actual meaning. If parity bit has got a change. If there is no change in the parity bit, if parity bit is unchanged, then I can understand that whatever you have sent to me from that side, I received it as it is, without any loss, without any error. I have received it. In that way, I can ensure it. So that is the usage of parity. Okay, so it finds application in communication. We call it as communication, or I can say like in sending and receiving data, in transmitting and receiving data. This parity will find its application. So as such, parity has to be generated ourselves before sending a data packet. Okay, I will generate in the sending side. Then at the receiving end, I have to what I have to do? I have to check it. That we call it as the parity checker. Okay. So as a whole, we are having 2 types of parity, two variants I said now. What are the two variants of parity is, one we call it as odd parity, another one is even parity. Okay, odd or I can say variants, two variants of parity is, one is called odd parity, another one is even parity. So in our curriculum, we are asked to implement a 3-bit odd or even parity generator checker. That is the actual experiment that has been given to us. Okay, so we will see to it how to do that. For that, I'll first share the PPT. Yeah, is the PPT visible to you?
Yes, sir.
Okay, thank you. I'll go to slideshow from beginning. Yeah, this is our lab U19 EZ212 Digital Electronics Laboratory. Agenda for today, it goes like this: review of the previous class portions. That's what we have done. We have to see what is a parity. I have given a small introduction. We will see the intro with the slides also. What is parity generator and what is parity checker? I said about this. So after the theory portions are getting completed, we will be entering into implementations. Implementation using logism, and virtual lab is not required. Logism, we will see it. And finally, I request all of you to remain in the class for attendance. So this is the lab details, and this is the actual syllabus. So now by today, by this week, we will be completing 4 experiments. That is serial number 3 up to that, because we have run with one pre-lab. Okay. So as coming Friday will also be a holiday due to Vinayaka Chaturthi. Today will be the only lab available for this week. So I'll be completing this experiment by today, and from next Tuesday we will be entering into the next experiment. Mini project, I said some points regarding mini projects in the last Friday itself. I hope everybody has started working towards mini projects. Okay, one fine day will come without any prior intimation. Okay, I may ask the batches to present the mini projects. So be ready for it, because you are not going to do any hardware here. You are going to do simulations system. That's all. Okay, so you're going to simulate your idea in logism. That's what you're going to do, or any other online simulator means using that you're going to simulate. That's all you're going to do. So kindly form a batch. You might have framed batches. You might have chosen your area. You might have chosen your experiment which you are going to do, and I think you might have handed over to your class representatives, Rahul, Franklin, and Priyadarshi, and you start working towards the completion of mini project. Okay, because one day will come and we may be asked to present for the presentation series for our theory courses. Okay, during that particular session, I'll ask everybody to present this particular mini project also. So be ready for it, because already we are running lagging of time. Okay. Okay. This is the course outcome. Again, parity generator and checker also is coming under combinational circuits. So CO1, we are in again implementation of various combinational circuits. So implementation means it comes under apply level. So apply level of K3 level of revised Bloom's taxonomy. Okay. Implementation of various combinational circuits. Now we will come to the actual term parity. What is a parity and what is its types? So a parity bit, we also call it as a check bit. So this particular parity bit is used to check. So that's why it has got another name called check bit. It is a bit added to a string of binary codes. String of means what does it mean? While sending some packets of data, if there is a characters, a combination of characters, we call it as a string, right? Along with that particular string, what I'll do is I will include this parity bit or check bit also. So these parity bits are the simple form of error detecting code. We cannot correct it because for error correction we have got some other code called Hamming code and all. That is also a separate procedure is followed. Parity bits will be there, but it is a modified version or extended version of parity bit. We call it as Hamming code. That is there available for error correction, right? But this particular parity bit or check bit can be used for error detecting. There are two variants or two kinds of parity bits. One we call it as even parity, another one we are going to call it as odd parity. So what we are going to do is just to learn this third point, you can understand. In even parity, the number of bits with a value of 1 are counted. Okay. In odd parity, if the number of bits with a value of 1 is an even number, the parity bit value is set to 1 to make the total number of ones in the set, including parity bit an odd number. In odd parity, what we will normally do is, if I am having a string of data, okay, I will count how many number of ones are there. How many ones are there, I will count it. If that particular number of ones is going to make an even number, then what I will do is I will add parity bit as 1 to make the number of ones in the string, including parity bit, as an odd number. Okay. If in case already I am counting the numbers, if it is already an odd number, then no issues. I can leave as such. I can add 0 to the parity bit. The same thing we are going to follow for even parity also. In even parity, what we are going to do is I will again count the number of ones in the data, sending data. If the number of ones is going to form even number of ones are there, means I will add 0 to the parity bit. But in controversy, if I am going to have the count of ones, number of ones as an odd number, I will add 1 to the parity bit so that I can make that particular odd number as a even number. This is the idea. So even parity la எனக்கு count பண்ணா parity bitோட சேர்த்து count பண்ணா even number of ones எனக்கு வரணும் அப்படிங்கிறது தான் டாஸ்க். அதே மாதிரி odd parity அப்படின்னா parity bit கூட சேர்த்து கவுண்ட் பண்ணும்போது எனக்கு odd number வரணும். இதுதாங்க கான்செப்ட். இதுக்கு தான் நம்ம வந்து we are going to design a circuit. Okay. See here uses. Where it finds uses is the parity bit ensures that the total number of ones or 1 bits in the string is either even or odd. Accordingly, there are two variants of parity bits. One is even parity bit, another one is odd parity bit. Okay. First, we will see odd parity. Odd, as our task is to design a 3-bit odd parity generator or checker. Okay, we will see to that first. So we will be seeing here what is the truth table. Truth table means actually what is the definition for truth table? A table in which outputs can be derived, okay, for different combinations of inputs, that we call it as truth table. From the truth table also I have drawn it in the slide itself. You can see A, B, C. If all the values are 0, 0, 0, then how many ones are here? No ones, 0 ones. Yeah, 0 is neither odd nor even. So I have to add odd parity P naught as 1. Then only I will count the number of ones, including the parity bit. It will make an odd number. Second term you see 0, 0, 1. That means already one number of 1 is there. 1 is an odd number. So add 0 in the parity bit. Okay, this is what we are going to do. Then for this particular truth table, we are going to derive the output expression. what is the expression for P0 using K-maps. Using K-map, we can do that, or by using ordinary method, we can do that. No issues. Then we have to implement that particular expression in a logic diagram. That is what is our task actually. Next is actually a even parity, 3-bit even parity generator or checker. Again, the same procedure. I will count the number of ones. If it is not making an even number, we have to make it as an even number. If it is already making an even number, no issues. We can add just 0 in the parity bit. So here also the procedure is truth table, output expressions we have to find it, derive it using K-maps or ordinary method, and we have to implement in the logic diagram. This is what is our plan actually. And we will implement using these simulators, either virtual lab or logism. And we will go for logism actually, okay? So this is actually the experiment which I have planned today, right? I'll stop sharing the screen now. You might have understood, and we will come straight away to the board. After completing the board explanation, we will go to the implementation part. Okay. Right. I'll switch on the camera. Good. Yeah, the board is visible.
Yes, sir, visible.
Good. So our task is to design a 3-bit parity generator or checker. Okay. So let me take first a 3-bit odd parity. Odd parity generator and checker. Okay. As I said, the procedure is to go for 3 steps. Number 1, truth table. Number 2, output expression derivation. And number 3, logic diagram implementation. Okay. So first, I am coming to the first step, truth table. So I am having inputs. How many inputs should I have right here? How many inputs I have to write? 3 inputs. Why? Because it is a 3-bit generator. How many output will come here?
1.
How many output pins? Only 1. That particular parity bit. Okay. So inputs, I am taking it as, for example, A, B, and C. As it is an odd parity, I am taking that particular term as P0. Right. So this is my truth table. So what are all the or how many combinations of inputs I can form it with 3 inputs? How many combinations?
8.
8 combinations, right? So I'll make some arrangement here also. So what are the numbers?
0,
0,
0,
0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally all ones. Am I right? Right or no? Right or wrong?
Yes, sir.
Okay. Now, can anyone tell what is the output values?
1.
1 second. Here, P0 is 1, okay? For the
0.
second combination, 0,
0.
third, 0,
1.
1,
0.
0,
1.
1,
1.
1,
0.
0. Very good, Priyadarshi. So, how Priyadarshi has given this answer is, as I said, we have to count the number of ones in the input string. Okay. Here you see the input string row wise you go with. Here I am having, for example, first case if I take A is 0, B is 0, and C is 0. Okay. all, the procedure is we have to count number of ones in the input string. So here the input string number of ones is 0. 0 is, I cannot categorize 0 as an odd number or as an even number. It is neither odd nor even. So I have to make it as an odd number. That is the procedure. So what I have to do is I have to add parity bit as 1. So including this parity bit only, I am going to send it for my application, sending it. Along with the data, along with parity bit only, I will send it. Okay, so number of ones now including this parity bit is 1. That means 1 is an odd number. In that way, we have to fill this particular output column. Okay, see 0, 0, 1 means already one number of 1 is there. 1 is an odd number, so no need to add P naught. Same case here. Here you see 2 ones are there. Number of ones is 2. 2 is an even number. How to make it as an odd number? Add 1 in the parity bit. You can get 3 number of ones, so it becomes an odd number. Here 1 is already there, so 0. Here 2 ones, so 1 has to be added. Here 2 ones, 1 has to be added. Here 3 ones already are available. 3 is an odd number. No need to add any extra 1 in the parity bit. So add 0. This is the first step what we have to perform as far as this particular design is concerned. Any doubt in writing this table? Any doubts? Okay, no sir, thank you. Now we will go to the second step. 1 minute. I'll so second step we will go into now, which we call it as what is the second step, ma? What is our second step? Yes, what is the second step? We have to go for K-maps for finding the output Boolean expression. Okay, here how many K-maps has to be drawn? How many K-maps? If you don't know the correct answer, no issues. You can guess it, no problem. It's a basic question from your digital. Here, how many in outputs are there? Only one output. So how many K-map has to be drawn here? Normally for output only, we will draw the K-map. Am I right? So we have to draw one K-map here with how many shells? How many shelled K-map we have to draw? Yes. How many shells should be there? Merlin? Yeah, 2 power 3.
8.
Yeah, 8. 8 means I can draw 8 shelled K-map. Okay, like this. Eight shelled K-map like this, and here I am taking A input. Here is BC. So 0 0 0 1 1 1 1 0, and here I am going to have 0 1. Okay. Now I am going to fill the blank boxes with the data. So 0 0 0 is 1. Then I am having 0 1 1 as 1. 1 0 1 as a 1, and 1 1 0 is a 1. Remaining shells are zeros. So this is what a kind of K-map I will get it here. Now can anyone tell what type of grouping can be formed here? What type of grouping can be formed? Any group can be formed here. Any pairs are there, or any quad is here. First of all, we have to see whether we can group all the 8 cells or not. Shall we group all the 8 cells? Yeah, Renuka Devi has given singles. Bachelor cells only we can do it, because here no pair is formed, no quad is formed, no octet is formed. Octet means all the 8 cells has to be paired. That is not possible here because we are having combinations of zeros and ones. We cannot make any octet pair. At least I will try to see whether I can do quad pair. Quad means 4 cells. That is also not possible because alternate zeros and ones are there. We cannot make quad pair also. So I will go for at least a couple, a pair can be formed or not. That is also not possible. You can check it horizontally, vertically, however, right? You cannot form even pair. So there is no other go. We have to go for bachelor cell pair or single cells. That means I have to pair each one separately. Okay, what will be the expression now? So this is actually I'm writing it for P naught. So what is the expression for P naught? Can anyone tell? What is the expression? If I take this particular one, what will happen? It will become A bar, B bar, C bar. If I take this one, it will become A bar, B, C. Plus if I take this one, A, B bar, C. And if I take the last one, it becomes A, B, C bar. Am I right? Right or not? Okay, with this expression, what we can do is the next question. With this particular expression, what we can do? See, you can even implement the same expression as such in the logism. But what will happen, number of gates requirement is large, because here we need one AND gate, A bar into B bar, one AND gate, B into C, another AND gate. So 2 AND gates, here 2, here 2, here 2, totally 8. 8 number of AND gates. Some number of NOT gates also required, because A bar, B bar, C bar, A bar there, B bar here, C bar again, it is required. So AND gates are also required. Along with that, we are in need of OR gates also, because summations we have to make. So number of gates will be more here. Okay. Instead, what I will try is whether I can simplify this expression. I will see to it. Okay. How simplification can be made is, from the first 2 expressions, what I am going to do is I am going to take A bar as a constant. Do you agree? If I take A bar as a constant, what is remaining is B bar, C bar in the first term, BC in the second term. Okay. In the same way, from third and fourth term, I will take A outside. Remaining is B bar C plus BC bar. Can anyone tell what is BC bar plus B bar C? What is that particular gate directly? A B bar plus A bar B. What is that particular gate? It is nothing but XOR. Yeah, Priyadarshi, you are right. So here it is actually XOR. So what happens is, see, what is this BC plus B bar C bar is XNOR. Okay. So XNOR notation எப்படி போடணும்னு சொல்லியிருக்கேன், ஒரு டாட் வச்சு சர்க்கிள் போட்டீங்க அப்படின்னா it becomes XNOR. XR எப்படி போடணும், ஒரு பிளஸ் போட்டு சர்க்கிள் போட்டா XR. This is the notation used. Okay. So this is XNOR. This one is XR. சரி. There is a relationship connecting XNOR and XR. என்னன்னு கேட்டீங்கன்னா, if I take the complement of XR gate, I will get XNOR gate. If I take the complement of XR gate, I will get XNOR gate. So நான் என்ன பண்றேன் அப்படின்னா, இந்த XNOR இருக்கு இல்லையா, இதை வந்து XR மாத்துறேன். So it will come in this way. Do you agree? One second, I will write and take the, yeah. Do you agree this? Yes or no? So this XNOR is a complement of XR. So B XR C, the whole bar. That is what is XNOR. This is remaining as such. Now you look at the term A bar. You take this particular entire bracket term as a single term. So A bar B bar plus AB. How it looks like. Again, it is a XNOR operation. So A XNOR B XR C. In this way I can write. Is it okay? Any doubt in this expression? See, A term is A as such. In the place of B, we have to write B XR C. So this is XNOR operation. சரியா? ஏதாவது டவுட் இருக்கா ராஜா இதுல? இதை வந்து இப்போ எக்ஸ்ஆர் யூஸ் பண்ணி எழுதணும்னா எப்படி எழுதலாங்க? இப்போ எக்ஸ்ஆருக்கு எனக்கு ரிலேஷன் தெரியும். இதை எப்படி எழுதுறதுன்னு சொல்லுங்க பார்க்கலாம். ஏ பி சி இங்க வந்து கண்டிப்பா எக்ஸ்ஆர் தான் வரும். இங்கேயும் எக்ஸ்ஆர் போட்டுட்டு ஹோல் பார் போட்டுக்கலாமா? whether this is correct or wrong. A XR B XR C the whole bar போட்டுக்கலாமா? Yes guys?
Yes, sir.
Okay, so this is what is the output expression for a what is it? Odd parity generator checker. Now இப்போ என்ன சேஞ்சுங்க இந்த எக்ஸ்பிரஷனுக்கும் இந்த எக்ஸ்பிரஷனுக்கும் நம்ம என்ன பண்ணிருக்கோம் டிசைன்ல? நான் இங்க சொல்லியிருக்கேன் எத்தனை நம்பர் ஆஃப் கேட்ஸ் நம்ம யூஸ் பண்ணணும். லாட் ஆஃப் கேட்ஸ் will be used, but what happens here? How many gates are required? Only 2 XR gates are required along with one NOT gate. Do you agree? So இந்த இடத்துல ஒரு XR gate A XR B கிடைச்சிரும். இங்க ஒரு XR gate. So A XR B XR C கிடைச்சிரும். And the answer for not putting abina, you can get the total expression. So how you look at how many gates has been reduced now. Number of gates has been tremendously, it has been reduced. Do you agree with this? Any doubts in this now? Now the final step is we have to go for லாஜிக் இம்ப்ளிமெண்டேஷன். சரியா? லாஜிக் இம்ப்ளிமெண்டேஷன் நான் போறதுக்கு முன்னாடி அதை நான் வந்து அங்க வந்து பண்ணிக்கிறேன். இதுல டயக்ராம் உங்களுக்கு வரைய தெரியும் இல்லையா? ஜஸ்ட் யூ டேக் ABC இன்புட்ஸ், யூ டிரா 2 XR gates, you take the NOT gate at the output, you can get the output for odd parity. Okay, இப்போ இதே கான்செப்டை நான் ஈவன் பேரிட்டிக்கு போடுறேன். என்ன ஆகுதுன்னு பாருங்க. நான் இங்கேயே மாத்திடுறேன், நீங்க தனியா எழுதிக்கிங்கப்பா. சரிங்களா? So I'll go for even parity. Even parity இதே மாதிரி தான். இங்க நான் வந்து PE அப்படின்னு எடுத்துக்கிறேன். இங்க வந்து அதுக்கு ஆப்போசிட்டா வரும் ஒன்ஸ். எங்கெங்கெல்லாம் 1 வரும், இங்க 0 வரும், இங்க 1 வரும், இங்க 1 வரும், 0 1 0 0 1. Okay, so opposite of odd parity. So here K-map also going to change, right? இதெல்லாம் எழுதிட்டீங்க இல்லையா? erase பண்ணிடலாமா? Shall I erase?
Yes, sir.
Okay. So நமக்கு syllabusல வந்து only 3 bit has been asked. The same thing has been asked for 4 bits. Again the same procedure you have to perform. Okay. இப்போ நான் வந்து K-map I am drawing it for even parity. So again 8-shelled K-map. Here A B C 0 1 0 0 0 1 1 1 1 0. I am filling the data. This is 1 here. 0 1 0 is 1. Then 1 0 0 is 1 and all ones are ones. Again alternative zeros da. So ingayum vandu bachelor pairs da form panna mudiyum, no doubt. So what is the expression for PE now? A bar B bar C.
B bars.
A bar B C bar A B bar C bar A B C. Do you agree with this? இப்போ எதை காமனா எடுக்கலாங்க? ஃபர்ஸ்ட் ரெண்டு டேர்ம்ல I will be taking A bar common. What is remaining? B bar C plus B C bar. From third and fourth term I will be taking A as common. What is remaining? B bar C bar plus B C. இப்போ அதே மாதிரி தான் பாருங்க. A B bar C plus B C bar, we can write it as a XOR operation. So B XOR C plus A into B bar C bar plus BC, we can put it as a XNOR gate. XNOR again XOR ஆ மாத்துனீங்க அப்படின்னா என்ன ஆகும்? XOR complement. இது எப்படி இருக்குன்னு பாருங்க. A B bar sorry A bar B plus A B bar மாதிரி இருக்கா? அப்ப எப்படி என்ன எழுதலாங்க? A XOR B XOR C. அவ்வளவுதான். This is what is my even parity. So என்ன difference odd parity க்கும் even parity க்கும்? Even parity பிட்டுக்கு நீங்க complement எடுத்தீங்கன்னா போதும், you will get odd parity. Do you agree with that? So I can write
Yes.
like P naught is PE bar. Okay. So again, if you draw some logic implementations, that will be over here. Any doubt in this odd parity and even parity part?
No, sir.
Any doubts? Shall we move on to the implementations? Yes. Okay, we will make a move to implementations. Now we will stop sharing the video. I'll go to screen share. Yeah. One minute. I'm sharing it. Where 20. Okay. Yeah, is the simulator visible?
No, sir. Now
Yes,
it's
sir.
visible.
Yeah. Okay. Thank you. It's visible now?
Yes, sir.
Okay. So we will straight away go to the project, analyze circuit. Inputs, we have to define it here. What are the inputs? A, B, C are the inputs. I have added it. I'll go to now outputs. What are the outputs? First, we will go for odd parity. Okay. Shall we go for odd parity or we will go for both at a time?
One by one, sir.
One by one. Okay. So P naught we will go for. Otherwise, you take it as P odd. No problem. It's our notation. We can name it anyway. I am adding it as output. Table now it becomes X only. Why? Because we have not defined any functionality. K-map will also be empty. Okay. Now I will go for expression. Here I will be explaining or writing the expression. What expression I have to draw? I mean, write it for odd parity. What is the notation for XOR gate? A. What is it? Caret symbol. Okay. A caret, B caret, C. A caret, B caret, C. If I do it means what I'll get? I'll be getting the XOR operation only. So I have to go for some tiled operation in front. If you put tiled symbol, it will become not of that particular value. Okay. Where is that tiled symbol? Either tiled or exclamatory mark. You can put anything. 1 minute. Where is the tiled? Yeah, here it is. Tiled. Yeah. Now it will art. Enter. See, A caret, B caret, C, the whole bar will be done. Now, if you go to the table, you can see what we have written it in the truth table. The same table will be filled out here. K-map also, you can see it. How grouping can be done like that. Is it okay? So with this particular base, now I am giving the option for build circuit. I'll name it as parity, maybe like odd parity. Right? My circuit has been drawn here very simply. See, 3 XR ABC and output. So you can check the truth table now. 0, 0, 0 means it becomes 1. If I make all ones, it will become 0 because odd parity. So 1, 0, 1, if I give it, it becomes 1 again because we have to make the number of ones to be odd. So no need to check even the truth table. So 0, 1, 1 means it is 1 because then only it will be made an odd number of ones. Okay, simple. That's all. Very simple circuit. Any doubt in this now? Okay. In the same way, I'll go for even parity. So I'll give build circuit or analyze circuit. Analyze circuit. Yeah. So here the inputs I'm taking it as again A, B, C. Outputs are just I'm taking it as like P even parity. Okay, I'm adding it. Now table will not be filled out. This thing will not be filled out. K-map. The expression I have to define it. What is the expression actually? A XR B
Carrots.
XR C. Caret symbol. Okay. So I'll get like this. Now you can see the K-map, right? You can see the table also. Now with this particular base, if I give the order to build this circuit, it will ask for file name. I'll give it as even parity. So it will draw. Same kind of circuit, P even. So 0, 0, 0 means 0. If I make anything as 1, output is 1. If I make all as 1s, output is 1. So in this way, you can check the operation of this thing, right? Any doubt in this now? Any doubts, Pa? In implementation? Very simple. See, either you can go for project and you can give analyze circuit, or you go for wiring and you can make the connections. Is it okay? அது செஞ்சு காட்டணுமா தெரியுமா எல்லாத்துக்கும்? வயரிங் எடுத்து எப்படி பண்றதுன்னு மேடம் சொல்லி கொடுத்துருப்பாங்கன்னு நினைக்கிறேன். அதில் ஏதாவது டவுட் இருக்கா? Whether I have to design it using the wire or using the basic gates? See, my sincere request is you have to sit and practice it with this particular simulator. அப்பதான் உங்களுக்கு அது ஈஸியாகும். வாரம் பார்த்தீங்கன்னா நம்ம ஃபேக்கல்ட்டி சொல்லித்தரதை மாத்திரம் லிசன் பண்ணிட்டு இருந்தோம்னா நமக்கு அந்த ப்ராக்டிஸ் கிடைக்காது. சரியா? நீங்க இந்த டூல் ரெடியா இருந்துச்சு, லேப்டாப் உங்ககிட்ட இருந்துச்சு, இந்த சிமுலேட்டர் நான் டவுன்லோட் பண்ணிட்டேன், இன்ஸ்டால் பண்ணிட்டேன் அப்படின்னா யூ ஸ்டார்ட் ப்ராக்டிஸிங் இட். அப்பதான் உங்களுக்கு அந்த இது எங்கெங்க இருக்கு, எப்படி பண்ணணுங்கிற இது தெரியும். வாரத்துக்கு நாங்கள் 2 நாள் வரோம், 2 நாள் மட்டும் இதை காட்டிட்டு போனாலும் அதை லேர்ன் பண்ண முடியாதுங்க. யூ ஹாவ் டு ப்ராக்டிஸ். ஓகே ஓகே, வித் திஸ் I'll stop sharing the screen, hoping that you don't have any doubt. So we have came to the end of this particular experiment. Okay, anybody has got any doubts? No, sir. Okay, thank you, Merlin. Thank you, Renuka Devi. Thank you, Priyadarshi. Okay, then, thank you so much for patient listening. We will once again meet on next Tuesday, because coming Friday is a holiday. Next Tuesday, we will meet with next experiment. Okay.